There are many applications that integration can find its use in. In H2 syllabus, we are interested in two particular types of applications. Number one, the area under a graph, and number two, the volume of a solid of revolution. In this video, we will first focus on the area of graphs. Simplest case, we have a region bounded by a curve, either the x or y axis, and a pair of vertical or horizontal lines, as shown in these two diagrams. To find out the areas of these regions, we simply have to use the following formulas. For the left diagram, we can make use of the formula A equals to integration of A to B y dx, which is the same as integration of A to B fx dx, if the graph is defined as y equals fx. Now for the diagram on the right, we will have to change the formula slightly to become A equals to integration of A to B x dy. And now since y is defined as y equals to fx, we will have to find out what is x in terms of y. And from our functions chapter, we will know that x is actually equals to f inverse of y. Or simply we can just call it another function of y, gy. So we have integration of A to B of gy dy. Now, by using these two formulas, we will be able to find out the areas respectively very easily. Example 1, we are told that the region is bounded by the graph y equals ln x, the x-axis, and x equals to 5. If we draw the graph out, it will look something like this. And the region that we are interested in will be bounded between this x-intercept, which is at x equals to 1, the vertical line x equals to 5, and this shaded region is where we are interested in. And since we are asked to find out this area using the formula A equals to integration of y dx, we can simply just do a direct substitution of the formula to get A equals to integration of 1 to 5 ln x dx, which we have to integrate using integration by parts. And this gives us x ln x from 1 to 5 minus integration of 1 to 5 x times 1 over x dx. Okay, now if we are going to perform integration for this second term over here and perform a substitution for this term over here, eventually you can work out and find that the answer is going to be 5 ln 5 minus 4 square units. Example 2, we have the exact same region of interest, but we are asked to solve for this area using the other formula, A equals to integrate x dy instead. Note that if we were to use this formula directly, we will not be able to get the required area. This is because if we look at our graph, the area of interest is highlighted in red from 1 to 5. And if we were to use this formula, what we will end up with is the region that I have shaded in blue. So this is not the area of interest. However, we note that the area of interest is simply the area of this rectangle subtracted by the area of the blue region. So therefore, by doing this subtraction, we can still find out the area very easily. Let's do it now. We have area equals to 5 multiplied by ln 5. This gives us the area of the rectangle since the breadth is 5 and the height is ln 5. Okay, so we have the area of the rectangle subtracted by integration of 0 to ln 5 x dy, which is 5 ln 5 minus integration of 0 to ln 5 ey dy. And we can solve this integration very easily to end up with the answer of 5 ln 5 minus 4 square units, which is the exact same answer as in example 1. Now these examples show that sometimes there is no right or wrong formula to use when it comes to finding an area, as we will end up with the same answers if both our approaches are correct. Sometimes the region of interest is bounded by two curves. This does not complicate matters much, as we can simply think of the region of interest to be a subtraction between the individual areas formed with the curves and the axis. For example, in the top graph over here, we can find out the area of this region very easily by finding out first the area formed with the top curve with the x-axis, and we subtract it by the area formed by the bottom curve and the x-axis. And let's call the top curve y upper, the bottom curve y lower, and the limits of integration to be a and b. And this area can be found using the formula a equals to integration from a to b, y upper minus y lower dx. Similarly, if I have this region over here, I can find it by finding the area formed between the right curve and the y-axis and subtract it by the area formed by the left curve and the y-axis. Let's call them y right and y left. And this region can be found using the formula a equals to integration of a to b, x right subtracted by x left dy. In example 3, we are interested in the region bounded by the curves y equals to x squared plus 2x minus 2 and y equals to 2x minus 1. By drawing out the graphs, we can see that the region of interest is bounded by the two curves and the lines x equals to minus 1 and x equals to 1. Therefore, to find this area, we can simply take the integration of the upper curve, which is y equals to 2x minus 1, subtracted by integration of the lower curve, which is y equals x squared plus 2x minus 2. And therefore, we have a equals to integration from minus 1 to 1, 2x minus 1, subtracted by x squared plus 2x minus 2 dx, which we can simplify into negative 1 to 1, negative x squared plus 1 dx, and we can calculate this to become 2 square units. Note that in this example, I have deliberately chosen the curves such that there is both positive region and negative regions within the area. However, what I want to highlight is that regardless whether there is a negative region or not in the area of interest bounded between the two curves, the formula that we have used earlier, a equals to integrate y upper minus y lower dx, will always be valid.